Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
Oh man, the video almost started again. That would have been really cool. That would have been the best live stream you ever saw. It's like the intro video, and then here's the live stream, and it's just the intro video again.
Okay.
It's an hour of just you repeating a 6-minute loop.
Yeah, that has slowly gotten a little
Less relevant.
less relevant. It's always like I gotta.
It's not
fix
even
that.
1 to. It's not even 1 to 3 anymore. It's 1:30.
It's
Get with the
more
get with the
130.
times.
Yeah, more 130 and all that stuff. And no one's spamming the chat as much, so maybe that's working.
I bet that is the one thing that's still accurate.
Yeah, that's right.
Everything else is inaccurate. For example, we don't sell electrochemistry products anymore. We sell pizzas and top hats.
Yeah.
But we're still recommending that you don't spam the chat. That's the only part of the intro video that I can confirm is still accurate. By the way, you appear to be Bigfoot now. You're blurry and I can't see.
Oh, I'm blurry.
You. Yeah.
I just gotta move in and out a little bit.
There you go. You got to move in and out until you become completely one with the background.
Yeah,
Which,
that's right.
By the way,
Is happening
is the Electrochemical Society. So see that transition right there?
Yeah, that's right. Yeah. So before we start going into questions, and hello everybody, not next week, but the week after. It's actually the week of Memorial Day in the U.S. In Seattle, we will be at the ECS meeting. Myself and my other colleague Tim will be there. So if you're in Seattle or if you're attending the ECS meeting, you should definitely stop by the Pine Research booth. We have a new booth actually, which looks super awesome.
It's so glorious.
Yes, it is so glorious. If anything, you should come and see what that booth looks like.
Yeah.
Let alone ask us questions about electrochemistry, which is all good.
You can also do that, but mostly you should just come and stare at the booth.
Yeah.
Alex and Tim are not that as good looking as our new booth.
Yeah.
It's amazing.
It is quite amazing.
Speaking of amazing things, we have a website. There it is. So this is our website. We've mentioned this for a couple weeks now, but we want to make everybody aware that here where you can like send a message and contact us and talk about how you want to buy every rotator in the world or whatever you want to do. You can also submit a live stream question. So if you have an account on our website, which we encourage, it's easier. It'll have your details and all those kinds of things. You don't have to fill out all the information. It just populates. You can see this is just some dummy information here. But once you do that and you select YouTube live stream question, you can tell us what your YouTube handle is if you want. So because obviously not everybody's YouTube handle is exactly equivalent to their name. And you can put files here if you want to ask us a question. The files thing is kind of a big part of it too, because I know that a lot of times throughout these live streams, Alex and I get these questions, and there's only so much we can do when you have a question about why does my voltammogram, what does this mean, or what about my impedance data? What am I supposed to interpret this, or how do I do circuit fitting? And it's rather difficult for us to answer those questions sometimes because we can't see your data from a comment on YouTube, but if you submit onto our website here, well, then you can put the data and then we can look at it. And it'll help us with answering some of these questions. So we do encourage you to go to our website, pineresearch.com. You can click the little contact chat icon up here. You can submit your questions ahead of time. we encourage that. And then the other thing is that the search feature is pretty neat too. So if you wanted to look for like impedance or something like that, and see all the episodes of our live stream that we've talked about, you can see all the timestamps, different videos and shorts. This is like other full videos. If you want to links to our YouTube channel, other articles and webinars that we've done on the topic, whatever you want to search for, you can find products, you can find links to our YouTube video on our website. So this search feature is really pretty nice now too. So just wanted to mention those things at the outset here.
Yeah, we sometimes get questions about like, oh, I want to learn about like how to make a TAFL plot. Well, you can also just search for TAFL plot or TAFL in that search, and it'll find every single time in our live stream we talked about it. So it's quite
We've talked
powerful,
about
very
TAFL plots
robust.
a lot.
Yes. Yeah.
Yes.
So should we got some questions. We did get one that was asked previously, or do you want to get to?
No, I think why don't you get to the Maximilian? I think that's the name. I think Maximilian is that's such a cool name, but it's so many letters that I don't know why I have a hard time.
Well, it's because it's got like 3 L's. I'm so used to just having like 2 L's in.
Oh, I wonder if it's a typo or it's just like million. Like his last name is Million. He put a million L's.
Lianas. Yeah.
Millianus. Anyway, he submitted this question, I want to say Wednesday or Tuesday. So it was earlier in the week. So we appreciate it. Again, we do try to answer the questions in with respect to the order they were submitted, or if people submit the questions on our website, we can prepare for them a little bit. But in any case, we do appreciate this. So the question was, I'll let you take it, Alex. I just wanted to mention it was asked on this YouTube live stream earlier in the week, and I made sure to save it because for some reason, this is another reason just to pitch, I suppose. Sorry, and then I promise I'll shut up. One of the reasons why we encourage everybody to submit the questions on our website instead of on the YouTube video ahead of time, like this video was scheduled. Like it's a live, we had these live streams, we schedule them, about a week or so out. And then you can type into the chat like in advance, but YouTube like removes the questions after some amount of days, like 3 days, they go away. Now I do my best to check our live stream, like the videos each day, to check if anybody asks a question, and just make sure I capture that. And the reason is because I know YouTube, for some reason, like gets rid of them. Like you would think that it would be in the chat still, and it's just not there. So I don't know why. So all that is to say that use our website because it would be a more effective way. It won't disappear. Like if there's a chance if you asked it and I just forgot or fell asleep for 7 days and forgot to check the thing, that your question would just be lost into the nethers of YouTube's database or something. I don't know. So,
well, thank you, Maximilianus77. He asks, "Hi, I am working with electrochemical gas sensors. My question is, I have an NO sensor using oxidation in an electrochemical cell. My goal is to check the sensor's health using a small voltage pulse. I did some research. Let me get to the second part of the question. And I'm going to try the following. My cell has a bias of 300 millivolts. I will give it a pulse that changes this to 302.4 or 302 to 304 millivolts for around half a second. The response in my measurement current shows the response you discussed in your chronoamperometry video. A peak and decline back to the baseline. Can I tell if my electrolyte is dried out or my sensor has lost sensitivity based on this response? I saw some companies doing this online." So Maximilianus, this is a very good question, and thank you for watching the chronoamperometry video. I appreciate it. So moving the potential. So my main thought when I read your question was that moving the potential such a small amount from 300 to 302 millivolts or 304 millivolts isn't really that big of a voltage increase or a voltage drop. You definitely will see a little bit of a spike and a small decay because that just happens. But the amount of current that generates is probably going to be very small. I don't know why you have it set to 300 millivolts. I'm assuming that has to do with the oxidation of the nitrous oxide, the NO, and for the glucose sensor to work. And you're trying to pulse it to kind of learn a little bit more about your sensor. So my first thought is I don't think that pulse is big enough to really see something appreciable. It feels like it would be in the noise, the current that you'll get. If you're getting a continuous like 100 microamps of current and then you start to see like, oh, I got like 5 microamps. It's like, well, a 5% change in the current is pretty small. You know, that could also come from other things. So that's small of a change. I would go a little bit larger. I would go maybe at least 10 millivolts, maybe a bit higher. And you always want to make sure that whenever you're stepping the potential, in these types of things, you can usually, if you're doing it diagnostically, you don't want to step it so far out that other reactions are going to happen. You could irreversibly be doing something to your system. So that's kind of my thoughts about it. You usually sometimes might pulse the potential by 10 millivolts, and you don't want it to go beyond a certain like Faradaic region. But your question really was like, if this is a way you can tell if your electrolyte is dried out of the sensor or if you've lost sensitivity based on this response. I think the only way you can really know that is if I don't know if you can determine if your electrolyte is dried out. I don't know whether or not that would actually affect it.
It kind of feels to me like if your electrolyte is dried out, it's actually a separate
issue altogether.
Yeah, exactly. It's a separate issue, and it's a separate sort of a diagnostic to the pulse change in and of itself, which is like if your electrolyte has dried out, I suspect your current would just be zero all the time.
Yeah.
Right? I mean, you're effective. Like consider if you have I'm just assuming that it's a 3 electrode system, right? If you have a working,
biosensor.
Right. So you have a working reference and counter electrode. What makes the whole electrochemistry system function is electrolyte present in between, right? Which is another way to say that there's electrical contact between all of the electrodes, ions moving in solution, et cetera. So if the electrolyte has dried out, there is no ionic or electrical movement between the electrodes in the solution because there isn't a solution. And therefore, electrochemistry is not physically possible. So you could literally almost simulate this practically by taking your potentiostat, taking your 3 electrodes, and just laying them flat on the desk and seeing what happens if you try to do anything. You probably get zero current.
Yeah.
Like nothing happened. Like you won't damage any electrodes. Nothing will happen because, I mean, the potentiostat might show 10 volts or, it might go to the rails of its voltage window sort of artificially, but nothing's really happening. There's just no current can pass at all because there's no electrolyte. So basically, whether it's 300 millivolts, 302.4 or 5 billion millivolts, I don't think whatever pulse you're picking, you should probably just get a flat line of zero current if your electrolyte is dried out. That's my guess. But now, I mean, I could be wrong. There could be other reasons why you still get current, maybe in some situation, or it's like partially dried, so your results look a little strange. But I guess I don't, like you, Alex, I kind of don't understand where the small pulse connects with that specific issue of electrolyte drying. I'm not sure.
Yeah, I agree. And then in terms of like losing sensitivity, you're talking about the stability of the sensor over time. You could try to use the pulse, but then again, you would need to do some experiments. Like, I definitely know about, to a certain degree, some people would do something like EIS to actually look at like, oh, is my is my sensor still stable after this long period of time, as a kind of non-destructive technique to evaluate, the health of it. But it's a research project. You have to see whether or not over the course of time of your sensor, you do this experiment, do you observe that, like, oh, the peak current starts to decrease when you do these like little chronoamp experiments every time you make an electrode, and you notice it goes down over time. And is that repeatable? If you make another sensor, does it start at the same current level and then continue to decay over time as you do these steps? Because then you could use it as a way to determine the sensitivity of your experiment, of your sensor. So
Yeah.
well, hopefully that is helpful. Hopefully you watch this video in the future, and then you can ask us more questions about it. Again, it's very helpful if you use that contact us submission form, because then you can send us pictures and even chronoamperograms of what you're looking at.
Yeah, it might help make it make more sense if you want to follow up on that with us. So
yeah. So Rebecca has a question from LinkedIn. Thank you, Rebecca, as always. Rebecca asks, hello, my question is about methods to determine the electroactive surface area of gold electrodes. Two I have found in the literature are the oxide reduction method using CV, and another is to use AFM to determine surface roughness. Any other methods, pros and cons, or things to be aware of when applying the methods?
So it's interesting because I'm not actually familiar with. I've talked about this, I guess, a good amount on live streams here.
Mm-hmm.
The only method like that's used probably again most often in electrochemistry for calculating the electroactive surface area is for platinum, and that uses the hydrogen adsorption desorption process. And the reason is because we know, based on literature and measurements done previously by lots of different researchers, that the specific charge associated with that process is about 210 microcoulombs per centimeter squared. The gold oxide, what is this? I just haven't even really, I'm not even aware of this one here, the oxide reduction method. So I guess this must have, it looks like there's a similar 390 microcoulombs per centimeter squared is a number apparently that is used for the gold, the reduction, gold oxide. Yeah. Okay. So without having done this myself, but I have done the platinum one. I could just sort of, I don't know that I can give a firm answer, other than to say that probably most people use the platinum method that I just described with the hydrogen adsorption desorption. That's used a lot, and to determine ECSA. And I would wager that in the literature, if you were to like determine or calculate like when someone has a platinum electrode, how often they use that electrochemical method to determine the ECSA, compared to how often they might use something physical or geometric, like you said, AFM, surface roughness, or they use like BET or a microscopy of some sort, right? That most people are using the electrochemical method to determine the ECSA. So because of that, I would propose that the best way for a gold electrode would be to use the CV method with gold oxide reduction. That would be my assumption. That would be my preference, to be somewhat analogous to the way people study platinum. The other reason for that is that by determining sort of physical geometric surface areas using whether it's AFM or whatever, you can run into some assumptions that may not always be true when you are doing the electrochemistry. So for instance, you might determine the specific surface area through like Brunner Emmett-Teller, right? And that's like X meters squared per gram. Or you'll do AFM, or you do microscopy and you do, you could do like an algorithm that sort of takes the surface, the roughness, or that takes the morphology of the particles, and you could use an algorithm, or you could do something to like calculate the effective, surface area or whatever. You could use the density of the material. You could use like material properties. Like there's ways you can do this physically, right? The problem that you get is that when you construct whatever electrode you're going to construct with said material, you're going to run into other things. Like you might have a binder. It might have, there's a substrate, like if you're doing like a glassy carbon disc or carbon paper or carbon felt or a silicon wafer, whatever it is that you have as a substrate, like some part physically of your electrode material will have an underside, right? That will be stuck to the substrate. So already there's some like fudge factor, some unknown amount of the geometric surface area that will be, let's just say, relatively inaccessible because it's on the bottom, right? It's stuck to the substrate. How much of that? Well, if it's a perfect sphere, it's not a lot. If they're flat wafers, it's, you don't know. So there's definitely some uncertainty associated with using just a geometric surface area calculation, because how much of it is actually there. And then, like I said, the binder thing is a big one. Like if you're using any kind of glassy carbon, any kind of carbon paper, carbon felt, whatever, you often have to use like a Nafion suspension of something, and it kind of acts like a glue, basically. It's sort of the state of the art. It's used almost all the time. There's an open question that I've had since graduate school that I've never been feel like has been satisfactorily answered, which is how does that block any part of the electrode surface as well? Because it's like, if I have to like get my catalyst stuck to a substrate, well, something has to like glue it there, stick it there. Does that have any impact on its electrochemical performance? It might. If so, how much? Well, now it's like you multiply the surface area by 0.7 and you're happy. 0.8. This is engineering at its finest. You just make some random number and then you're happy, right? But it's definitely an open question about how effective that is. So when you do the electrochemical method, there's going to be errors, like no matter what you do. And, you're at the mercy of how sensitive your instrument is and how well you made your electrode. There's a lot of things that can cause error. But effectively, you can make the assumption with I would say more confidence than a simple geometric calculation that the current you're getting is because of the catalyst there. Like all of those things I talked about, like however much current you end up getting for the gold reaction is going to be because that's the amount of gold that's present in the surface area that's available, right? So I think the electrochemical method, if you have this 390, that's a number you can use. That's great. That to me seems like a better method. It's more connected to the electrochemistry itself. There's definitely something that could be some error associated with that as well. But to me, that is a better way to sort of get at what's really present when your electrode is constructed. It's on a substrate, all those things. So that's my opinion, Rebecca. And I actually appreciate this a lot because, yeah, like I said, I just did a quick kind of search for this, but this has been the one thing that I've kind of had as an open question forever. And a lot of times it's been like people will ask about, various materials, like some, nickel iron cobalt complex or something. And it's like, okay, well, if it's hard to know like how to get the ECSA electrochemically for a lot of specialized materials, because I don't think that these, whether it's 390 for the gold or 210 for platinum or whatever, thankfully these are well known, well used, well studied electrocatalysts. So people have tabulated these numbers, but they just a a lot of these kinds of specific charges for whatever processes just haven't been tabulated for like any and all catalysts. So you're kind of stuck, I guess, having to use a physical sort of geometric surface area method to get, what can be assumed to be the ECSA in a lot of cases.
Another thing you can do in addition to this, if you want to just like kind of double check or make sure you're in the right ballpark, is if you have just a regular gold electrode and you're just doing CV of a well-characterized system like ferrocene or ruthenium hexamine, you can use the cyclic voltammetry data because if you know the diffusion coefficient and you know the scan rate, you can use the Randall substance equation, and you can let area be kind of your unknown, and that should at least give you a ballpark. I'm just talking like ballpark determination of the surface area. You could be off by like a factor of 2 or 4, but if you're like way out there, it's like, oh, it's several orders of magnitude different, then it's like, oh, maybe this method's a little off. But like usually because ruthenium hexamine is like a bigger molecule than oxygen, so it's clearly not going to interact with as much of the gold as oxygen atoms are. So you should, in principle, get. I'm assuming it would be more of like an underestimation using like using ruthenium hexamine than gold if you were to use that kind of method as a double check. So that's another thing.
Yeah, Rebecca says that the electrochemical method seems the best. Everyone refer back to a paper from 91 by Trussati. So Trussati, there's like done in Trussati methods. They're used for capacitances. That's it's like the pseudocapacitance kind of method, which I'm not like amazing on. Like I don't. You're determining how ideal effectively the capacitance is, something of that nature. So that doesn't surprise me that Trussati was contributed in that way. It's a similar thing for platinum, Rebecca, which I have that paper. I was trying to electrochemical. I bet you.
Oh, 1991.
It's this one's from 1971. It's even older. Because platinum, I think, is probably, I'm guessing, predates gold to a certain extent. I don't know if this is original paper. I'll just share it because we're on the topic. It's just kind of curious to me. This is by Biegler, Rand, and Woods. This should be sharing in just a second here.
Yeah.
So this paper here is from 1971. And this is, again, I don't know if this is the paper, but it's one of the first ones that I found where they kind of, at the very least, aggregated results from the platinum hydrogen adsorption desorption region to come up with that 210 number. It's in here somewhere, I promise. So this is the hydrogen. This is like it's all backwards. I don't know why they're plotting things weirdly, but anyway, it's like the Texas Convention, but also reversed. Like anyway, they usually don't plot it this way, but this is the hydrogen region here. You can see, and it's like an aggregate of the different. What is it? The different crystal facets or whatever that were used. So this is where they talk about it, right? To obtain the platinum surface area. And this is where the 210 number comes from. You can see it's right here. So it's commonly been taken as 210, a value justified on the predominance of the 100 plane or equal distribution of the 3 lower index planes. So this is, again, everything we're talking, I think the main point to make here is that everything we're talking about, whether it's what Alex said about you could use like ferrocene or ruthenium hexamine, you could make an assumption of the diffusion coefficient of whatever electrolyte you have, and you could solve the Randall subject equation for area. It's reasonable as anything else. You could do this with platinum or the 390 for the gold. You could do that. Stop sharing. That's the one. And it's like there's error no matter how you deal with it. Because even this 210 in the platinum, and I'm guessing that gold is a similar thing. It's like it's based on assumption of a bunch of planes. There's 208, 295, 147, 241. These are all numbers associated with different crystal facets of the platinum. And it's like 210 is like an average. So even then, using this number with the electrochemical method that everybody uses and assumes is like the most accurate is still an approximation.
Yeah.
So it's like, oh, well, then it's okay. Well, then I'm assuming a diffusion coefficient, and that might be wrong. It's like no matter how you do this, there's a lot of assumptions being made, and it's take it with some, as they say, a grain of salt. Don't worry too much. You're getting some number, but the error associated with any of these calculations is likely relatively high, right? So
yes. Okay. All right. So Rebecca, I hope that answers your question. Always great having your questions and regularly tuning in. The next question is how to master the electrochemistry portion of physical chemistry. Ask for a little bit more elaboration, saying that master implies build a strong foundation in concepts of electrochemistry. I'd say this is a more of a general question about how do you just get good at electrochemistry? That's really the crux of the question, I would say. So tuning into this live stream is an important part of building in and trying to learn stuff. Watching our YouTube videos as well, reading books, doing hands-on experiments. Learning electrochemistry is tough. Building a strong conceptual foundation and experimental foundation, it's hard. I don't even know where to start. I think when I started learning electrochemistry, it was just like, all right, just do a cyclic voltammetry experiment and see if you can get what was reported in the literature. And then as you fail at that and you figure out what you're doing wrong, you slowly learn more and more and more about electrochemistry and how to do things. But yeah, I don't know. There's a lot of resources and tools. I think it's based on the questions that you're trying to answer in, I'm assuming, a physical chemistry course. So yeah, I don't know. I haven't really given study advice about how do you master electrochemistry. There actually are masters of electrochemistry programs. In general.
Yeah, is it? Feels like it's mostly PhD programs, but I guess there must be masters.
There are, I believe, I know there's one. I think that's at Irvine. There used to be one. I think no, there's one in Oregon. University of Oregon offers a Masters of Electrochemistry program, and they just focus on giving you a master's degree, and it's focused on electrochemistry. There's tons of electrochemistry content out there. So, but yeah, Neil, if you have anything, it's a very general question.
No, it is. Honestly, some of the answer depends on how you learn best. To a certain extent, I would say that the way to learn anything is to push yourself a little bit beyond your capabilities. That's how anybody learns or grows or gets better at anything, is you have to stretch yourself a little bit beyond your current limits and or understanding. So to that point, you have to fail. Like you said, you're doing voltammograms and you sort of fail. I would propose that for learning electrochemistry, very often it really needs to involve experimentation. The problem is that if you're sort of in a class, you're not doing research, you're not necessarily doing a degree program, but you have some electrochemistry facets of whatever course you're in, if it's physical chemistry or otherwise. That practical aspect of it might not be possible, or at the very least, very simple. For textbooks, it's like the Barden-Faulkner textbook is, considered the Bible of electrochemistry, if you will. But it can be hard to digest. If you just take the Barden-Faulkner textbook and you just open it and start reading, It might be tough. It might be tough to kind of to I don't know, to understand it or to come to grips with the concepts, I guess. It's almost like it could be a hard book to digest, I guess I'd say, depending on your education level and your interest, maybe. Electrochemical methods, fundamentals, and applications is the name.
Yeah,
So,
they're on the third edition of the book now.
yeah.
You'll probably the second edition is probably like the most found. Although actually, as I visit labs, I find more and more of them have the third edition. Which
Yeah,
I'm
it
like,
takes
oh,
time for these things to like trickle through, right?
yeah. I just figured like I know there are differences between the second and third edition, but it's like, are there that many differences that people would buy like that? The second edition is super prevalent, and I'm
Yeah.
surprised that there's a lot of people getting like, I gotta get the latest edition. It had a couple changes in it. you
Well,
know,
I don't know if you're aware of this. The first edition, they only had current, no potential at all.
that's right.
So the second edition, they added potential. And
Yeah,
then the third edition, they added time. So now it's all three variables of electrochemistry, and there can't be a fourth edition because there's no other variables. So that's it.
I will also add the following book here. Hold on, it's
The Heinemann book.
textbook. It's the electrochemical engineering textbook, which is just called Electrochemical Engineering. That book is also.
It's just
Oops.
called electrochemical engineering.
I put that in the wrong. Oh, yeah. It's by John Harb and Thomas Fuller. And actually, if Rebecca is here, John Harb was at BYU. I didn't even realize that. So,
Well, look at that.
yeah. But I find that book is good in the sense it fills in some of the gaps that Barton Faulkner misses out on, because one is a true like electroanalytical chemistry book. The other one actually handles like the practical engineering, battery fuel cell, high current, applications, things like that. How to make a Tafel plot, those types of things.
Yeah, a lot of Barton Faulkner tends to be like, I think the things with Barton Faulkner that, like, for me, and again, this is more maybe personal for how I conceptualize stuff or how I like to learn or whatever. It'll be mathematical in a lot of cases. It'll be really theoretical, but then it won't like when there's a mathematical derivation in Barton Faulkner, they often skip a ton of steps, which can be fine. Which can be fine if you either don't care, math isn't like your mathematics, or derivations or those kinds of things aren't your like forte, or you don't really like it, or you just kind of want to know what's the equation to use or whatever. And this is pretty standard stuff for like a university textbook, I would say, is that a lot of times it'll be like, well, we start with this, and then after a few steps, and it's like equation 2 is the final answer. And it's like, just for me personally, I always find that a little less satisfying, because I like to see the steps so I can understand how I got from wherever to wherever. Oh, you switched on me.
No, sorry. I'm gonna switch again.
Oh, we're going back.
The internet plug like came out.
Oh. But yeah, I think the thing is, again, for me, it's like sometimes the understanding can be tough, because it's like it's almost like at like a little bit too high of a level sometimes in Barton Faulkner, where they present a lot of equations, but it's like I kind of want to know more fundamentally how things happen. Now that can be hard, because I don't know how many textbooks or sources really do a job of fleshing all of that out like really thoroughly. So what I'm saying is lacking, unfortunately. If that is something that you wanted, is not, I don't have a good solution for that. What I will say again, though, is that this very YouTube channel that you're on right now, a lot of the learning about electrochemistry involves kind of understanding the practical and fundamental kinds of techniques like cyclic voltammetry or impedance spectroscopy. And we have videos that describe those in like 10 minutes. right? So, of course, it's not going to be comprehensive. It's not going to necessarily cover every single thing you could ever want to know. But if you want to kind of get a good overview of what cyclic voltammetry is like and what a voltammogram looks like and why it looks the way it does, our YouTube channel should be a good resource for you. And, our website, the search that I showed earlier, you can search for cyclic voltammetry or something, and you'll find a lot of timestamps where we've talked about it during this live stream over the last several years. So, selfishly, we can suggest ourselves. We do all of this YouTube stuff to try to be a resource for for education and whatnot. So,
yeah, and on that same note, while some of our 10-minute YouTube or 20-minute YouTube videos go into details about cyclic voltammetry and impedance spectroscopy, we do have webinars that are much more in depth. So normally, like, I wouldn't spend a ton of time in a YouTube video talking about electrochemical, potential, but in a webinar where it's like, all right, I'm allocating a huge chunk of time to describing something, then yes, I'll talk about some of the more fundamentals about electrochemical potential and what really is current and how these electrodes really work. And so there's more depth that can be gotten, but you'll end up using a lot of tools. You'll use books, you'll use videos, you'll do experiments. We have workshops as well. Like, I would encourage you to, do an electrochemistry workshop, because sometimes you'll read something in the book and you're like, I think I understand this, but I think I need to talk to some other people about it to help me make sure I really know what I'm talking about. So there are aspects like that.
If you're at a university, maybe you're an undergraduate, maybe you're a graduate student, but if you're doing like a physical chemistry class or you're doing some other class and there's a module with electrochemistry involved, and you really want to learn more about it, there's probably at least one or two professors at your university who are doing electrochemistry research. It's certainly a topic that at most universities with chemistry or chemical engineering programs, there's at least one or two professors, maybe more, who have some aspect of electrochemistry involved in their research. So, some of this is really on you. Like, universities are great, obviously, places for you to like get the most out of it for what you want. Like, if you email a professor and you're like, I'm interested in knowing more about whatever, can I like come hang out in your lab? Can one of your grad students or postdocs just kind of let me watch them do research for a few hours some days or something? They'd probably let you do that. I don't know. Maybe some universities have rules or something, but I know that like when I was in grad school, we did stuff like that sometimes. You'd have undergraduates come in and do some research projects, or we had some people come in and tour the lab here and there. Like, most research labs are pretty open and accommodating and often welcoming of stuff like that. I mean, heck, if there's anything that PhD students and professors like, it's talking about their research. So, it shouldn't be too hard to get someone to talk about their research, no matter what. And then if they're doing electrochemistry, you can just, ask them to tell you all about it, and they see if they'll let you watch them do some stuff, and you can say, well, what is that? What's this? They'll tell you what the electrodes are and what they're doing and stuff like that. I feel like that should be within the realm of possibility if you're at a university. But that's not something that like everyone's going to do, right? And it's not something that likely you're going to get the professor inviting, right? You're going to have to seek that out yourself. So be bold, be brave, be willing to step outside your comfort zone and go ask some people some stuff, I guess.
Yeah, or you can just stay inside all the time and just and never go out. And
That's
it's
true.
not like that will be a decision that'll haunt you for the rest of your life
No,
ever
not at
again
all.
that
Yeah,
you didn't go out.
that definitely won't hurt you for the rest of your life. That's great. That's
Yeah, yeah.
super not ominous at all.
All right. Well, it doesn't look like there are any other questions that have come in the interim. So, so Neil, how are you feeling? You want to filibuster a little bit, waiting, or you want to call
Well,
the?
there was this one question
Oh,
from
okay,
Vinny Jin that was like a while ago, and I don't
okay.
really know exactly when we got it. To be honest, it's been some time.
Oh, it's been a while. Yeah,
Yeah,
we got that question a long time
but it was
ago.
kind of an interesting question. I thought I'd kind of touch on it, and it might even be mostly through the the lens of whatever battery stuff. Even though this question might not have been specifically asking about that, but the question was, when running a script with different methods such as CV and EIS, would you recommend reading or applying OCP between steps? I think applying OCP helps to reestablish the interface concentrations. Um, so to a certain extent, the answer is yes. Um, but I think that it kind of depends on the type of experiment that is being run. So the reason why this question is kind of interesting, or one of the reasons why I find this question interesting from the lens of battery research, and that is because if you're talking about running OCP with like a 3 electrode system, right? With a, let's say, a small electrode, surface area or whatever it is, and a typical counter and reference electrode. Very often, your OCP measurement is just going to, whatever it is, it's going to be relatively steady. You're going to get, over some amount of time, it's going to be this. Now, if you run a CV and then you take EIS, yeah, maybe the beginning of your EIS, there might be a little bit of like a drift or a lag if whatever you did to the system was kind of dramatic or something like that. But for the most part, if you have a pretty stable system, the OCP is going to be not all that interesting, and in some cases not like super necessary. Most of the time, running the OCP is useful for only just a couple of reasons. One is to make sure you have a stable potential at all, which can be an indication that all of your cells and electrodes are connected properly. So that's a good. I mean, that's a really good thing, because if your OCP was like this, it was going off to craziness, that would be frowny face. Bad idea. Like, that would be an indication, hey, something isn't connected properly. So it's a good thing I ran OCP. It's a passive technique. It's not going to damage any electrodes. Before I try to run CV and I forgot to connect my counter electrode, something like that. Okay. Where the OCP can be really quite useful in another situation is when you have a really big electrode or you have a very large time constant. Okay. Those things sometimes can be one and the same, but this is why batteries sometimes fall into this situation. So for batteries, for instance, tau, the time constant, is often quite large, which means that this is R times C, and because they have a large capacitance, they have a large time constant. And so what you get is that after a CV or an EIS or a charging or discharging step, the OCP of a battery can take a very long time to steady out. Okay, this could be as much as like, let's just say 10 minutes. 10 minutes. Okay. So in this case, what you have is a situation where, yes, absolutely, having OCP in between some of these steps can be very useful, and actually in some cases necessary, because there's there's terms used for this. You could call it the diffusion or the relaxation or things of that nature. reestablishing the interface, whatever sort of terminology you might end up using in a different whatever context you're looking at. But basically, because the time constant's so large, because there's a large surface area, because there might be a lot of material, there might be a lot of porous microstructure where material is diffusing in, has to diffuse out, whatever it is. After and in between running steps, you might need to have a relatively extended OCP step before you run the next one. And that is, also because, like, frankly, there could be a difference between this, E like naught or whatever where it started, and this, whatever E final, and that could make the difference between whether I do my impedance experiment or start my next, scan or charge discharge at that potential versus this potential. It could make a big difference because I really don't. This E0 is the what happens to be the initial open circuit measurement, or the potential that the system is at, but it's not the potential of the system once it's fully relaxed. So all this is to say that is whether you should run EIS, OCP in between, a series of tests. In one case, the answer is absolutely, because it can help you, really find out if you have connection problems. So it's almost never going to hurt you because it's a passive technique, and so it's not a bad idea. And then in other cases, it's going to be absolutely critical because if you have a large time constant, you have these big systems like batteries is one example, capacitors sometimes as well. You can really benefit from having a long OCP step to make sure that the potential is stable in between your next steps, I guess, or your next experiments. So just wanted to talk through some of that, again, through the context of batteries. It becomes a little more obvious why you have to rest in between experiments. But yeah, so there you go.
There you go. All right, we did have another question come in. Asks, can you comment about aptamers and the need of square wave voltammetry need for them? Yeah, I can comment at least a little bit about it. I don't know a lot about aptamers. Aptamers, generally speaking, are these kinds of, I believe it's a DNA molecule, or it's a kind of DNA-like structure that can be crafted to kind of fit the mold of any kind of target molecule. And then people put some kind of redox probe on the end of the aptamer. And so this aptamer exists as part of a self-assembled monolayer. And I can just draw this just to kind of give you a general general picture in my head, at least, about what people are talking about when they talk about aptamers. But if you have a surface, like an electrode, an aptamer there'll be some kind of head group, and then there'll be some weird kind of chain, shape, and then there'll be like a redox probe on it. Just put like a little X on it. And they'll have, let's see if I can select this. So I'm going to try to do my best to erase these parts here, only taking the useful aptamer, if you will. There we go. So you have this. So you have a couple of these guys. You have a bunch of them, all over. And maybe I'll just move this out so the spacing's a little bit better. So you have a bunch of these guys, and you have a molecule that can fit, right? So you have some molecule that uniquely fits into the aptamer based on its design. And when that happens, this guy will go towards the electrode surface, and then you'll get an electron transfer reaction. So aptamers are very neat in the sense that it literally doesn't matter what you're trying to sense. if you can create an aptamer that has this kind of geometry that can fit the target molecule, then it doesn't matter what that molecule is, you can detect it electrochemically because you've tethered this redox probe onto the, the specific thing. This usually exists. There's usually other self-assembled monolayers with, say, maybe you have like OH groups, you have mixed monolayers. The problem with aptamers is that they're often not very stable over long periods of time, so they don't actually get a lot of commercial use because things can attack these and degrade them. And so there's a lot of research in like trying to stabilize these aptamers with other types of, molecules and other kind of backfilled species. So that's fundamentally what an aptamer is, and kind of what the research is like, trying to make new target aptamers to target specific things that what you want to detect, and being able to stabilize them. Now, square wave voltammetry is used instead of, say, cyclic voltammetry because square wave voltammetry is a bit more sensitive. You're only looking at surface-bound species. So at the get-go, your detection is very low. And while I haven't done the research, most people use square wave simply because this is an analytical technique, and what you're ultimately trying to do is just detect it. You're not trying to get any useful, like in CV, you really want to make sure, it's kind of a diagnostic tool. Like, oh, what's the E1/2 in your CV? What's the peak potential? What's the peak current? You're doing all these diagnostics, and CV is very fast. You can have very fast scan rates. In square wave, the potential waveform, square wave is actually, a lot of people believe square wave is actually superior to CV because it's really quite as fast, and it really gives you very low background currents. You can do, and actually you only need to do like one, you only need to go in like one direction, because in the square wave, you collect like 3 data points. So in the square wave, which looks like this, you're collecting data points like here and here and here, and you're looking at like, you're getting like the forward wave, you're getting the reverse wave, and you're getting like the difference between these two. So you end
Alex,
up getting a lot of data.
Just to cut you off, just what you're talking about is pretty much exactly this. Now, I just wanted to mention the person also just said, can you please elaborate on the sensitivity of square wave, like how it cancels background noise? I just wanted to, what you're talking, you can elaborate on this, or maybe
sure.
Fresh. Just the person just asked precisely what you're talking about now, so I just
okay, yeah. How does it cancel out background noise?
Yeah.
Good question. So there's kind of two elements to the cancellation of background noise. One is that unlike cyclic voltammetry, when you charge the electrical double layer, so there is an electrical double layer that exists here, that double layer has a charging current. So let me just move this up a little bit. So we can maybe, you know what? I can make it a little bit smaller too. Yeah, there we go. So you end up getting this kind of charging current that, like in chronoamperometry, that decays over time, right? So this is time and this is current. So whenever in cyclic voltammetry, when you sweep the potential like this charging current never really has time to decay. You're constantly going up or down in potential. This is like potential. This is potential, and this is time. But whenever you do a pulse technique where you pulse and then you wait, if you collect a data point here, right? So if you're collecting the data point here, this is the charging current's already disappeared because you're collecting the data point at like this point in the chronoamperogram. So all the charging happened like at this point, right? You're looking at Faradaic processes down here. So you're able to remove the background current simply by waiting long enough for the current to decay. And the time it takes for that current to decay is 5 times RC, the solution resistance times the capacitance of your system. So that's like the time. 1 RC time constant represents like 60 something percent chance or percent charged or discharge. And so 5 RC is the time for it to completely, like 99.9% charge or discharge. So for the double layer to charge up, the time it takes for it to completely charge is 5 RC. And as long as the time that you wait for this pulse in the square wave to occur is more than 5 RC, then you've removed background capacitive current. So that's part of it. The other part is that if you're looking at differences in the current, right? So let's say you're looking at the difference, right? You subtract, actually, you'd probably subtract these two. You take this current here. Actually, I'll use red for that. I think you take this current here and this current here, and you subtract them. So if there was even a background Faradaic process that was occurring, that let's say there was some mild gold oxidation or something that was happening in your potential region, but it was kind of a background signal, you could remove it, because if you take the difference between these two guys, if this is a background process between them, that current also gets removed. So you're only looking at the processes and the current that is associated with this increase or change in the pulse. And that's another way that square wave allows you to remove background signals. So let me see.
I think that's a good point to make too. You stressed that in your voltammetry series, I think, because you talked about about, is it square wave or just pulse in general? But
I talked about differential pulse because
yeah,
at the time, and I still feel like square wave has a weird diffusion layer profile.
Yeah, it's a little bit strange.
Mm-hmm.
But the I think the main point, right, is just that. It's that people often, I don't know, not think about it wrong, but almost like underestimate or under report this background process, this background subtraction. It's not just like non-Faradaic or charging current that's subtracted. It's also Faradaic current, if there is any. It can subtract that. So what it really is doing in a pulse method in general, and there's different ones, but for the most part, they're all similar in that they really highlight the difference that occurs within the width of the pulse, within the how high the pulse is going, the difference in whatever Faradaic process is occurring within that window.
Yes. Yeah. Yes, that's
if
right.
I said that correct, I think.
Yeah, I think so.
Hopefully, I said it the way I meant it in my head.
So the continuation, I guess, of his question is, why can't you just do a single step? Yeah, you could just step the potential once if you want, but there's only that's just a chronoamperometry experiment.
Yep.
So you could do that, but your ability to figure out like where is the E naught in your system. Like one of the advantages of square wave is that you're able to figure out like E naught values, and you can even get ratios of diffusion coefficients. You don't, like, when you do one step, it's like there's not that much information. It's just a chronoamperogram. So you can do that. But yeah, if you wanted to, like, you could absolutely do that. It's just a matter of collecting the current at what point.
Mm-hmm.
It says also current profile inverts when step polarity reverses. So subtraction actually increases background noise, isn't it? So that's not the case, because you're going in the other direction, but the current is also moving. Like if the steps are moving like this way going up and they're going this way going down, it's like you end up doing another like double subtraction. Like you subtract a negative because you're going to be getting negative current going the opposite direction. So one of those is going to become positive when you subtract them. You're always looking for differences.
Yeah.
So will that increase? So, but to your point, does it increase the background noise? And the answer is still no, because you are looking for just like differences between these 2 points. And Square Wave also provides you with the raw data as well. It provides you with the raw, like just the forward pulses, just the reverse pulses, and then it gives you like the difference between those two. I'm pretty sure it's the difference.
Yeah. This is just an algebra thing. Don't get confused about negative current and thinking that it's all going to go super negative forever. It's a difference. So when you have like the pulse going the positive direction, and it's like you have like 10 microamps and then minus 9 microamps or minus 10, so it's like 1 or 0. It's like 10 minus 9 or 10 minus 10. And then when you go in the other direction, it's like minus 10 and minus 9. The difference between those two does not equal minus 19. It's still 0 or 1 or minus 1, right? Like negative 10 minus a negative 9 is negative 1. This is right. This is just math. Like you're subtracting. It's a negative number, and then you're subtracting a negative number, which is like adding a positive number. So it doesn't just go. You don't just get like a ever larger negative number, right? It's still a difference, and just simple algebra, it still gets close to 0. It might be slightly negative or slightly positive, but whatever. Yeah. So it looks like he might be clarifying.
Yeah, he might clarify.
So I just wanted to clarify that if you're thinking about negative numbers, but it doesn't appear to be what precisely he's thinking about. Feel free to clarify. I'll kind of address this next question while we wait for you to clarify. Take your time.
10 minus negative. All right, so he's saying,
it wouldn't be 10. It would be minus 10.
So it's 10 minus negative 9.
Well,
and that's 19. And the difference between 10 and negative 9 is 19. So it's a big difference between those two.
Right.
So that's correct. If you were getting 10 microamps in one case and then negative 9 microamps in the other, the difference is going to be 19. Yeah. So you're going to see that actual difference between those two.
Yeah.
And so that also brings up a very good point, which is that there's going to be differences in the current near the E naught of the reaction, right? That's where you're going to see differences. When you're at a potential range where nothing is happening, where there's no electron transfer reactions, you're going to be taking differences of nothing. So the difference of nothing minus nothing is going to give you nothing. And as a result, you end up getting nothing. So this is
that's very profound. Nothing.
Very profound.
Take away nothing. Add nothing.
Add nothing.
Multiply by nothing, and you get
nothing.
Oh, that's so good.
So, and that's why the background is so low, because that's the reason why the background is so low. It's nothing minus nothing, but the moment you add something in there, that gets big, right? Because it's being subtracted by a bunch of nothings. So you really got something when you're comparing it to nothing. All right, he's getting a little bit. Let's see. All right, current polarity for the positive voltage step will be positive, and for the negative step will be negative. It's directly capacitive current. Okay, yeah. So at those steps. So we're talking about the very edges of the square wave, right? We're just talking about like at the point. So if you wait it out, there's no background. Okay. All right. Yes. All right. So we understand it. That's good. If you wait it out, there's no background. Yeah. No, that's the big thing. And that's the advantage of square wave. You wait it out. And it doesn't have to be, 5 RC actually isn't that long. An RC time constant can be on the maybe hundreds of microseconds time scale if you have like a small electrode and you have a very low like solution resistance. So 5 RC actually isn't really that long for your steps to occur and stuff like that.
We're talking milliseconds is long enough. So
Yeah.
that all of it's just background, Faradaic and non-Faradaic processes, basically.
Yeah.
Like
Yeah.
the Cottrell decay has already completed by a millisecond most of the time,
Yeah. Yeah.
And most of your resolution for your potentiostats, for your pulses, are going to be longer than a millisecond. You'll have a pulse that's like 50 milliseconds. I'm just making up a number, something like that, right? That's usually about what it is.
Let's see. And so he's waiting. He's just like, okay, if we wait, why the need of double step? That part is not still.
I think
fully understood.
it seems like what he's thinking is that, and correct me if I'm wrong, right? Ratad Garwal. You're thinking that if we wait longer than 5 RC every time, why isn't it always just 0 all the time? That's what it seems like you're feeling is like if what we're saying, like what Alex and I are saying, is like, well, you're waiting long enough, so all of the background, everything's decayed down, so wouldn't it just always be 0? That's what it feels like you're interpreting our answer. If that's correct, then the answer is that dying down of the background processes or whatever, that whole thing, the level that it dies down to is not the same depending on the potential of each part of the pulse. So the double step, so to speak. So like, why do I step up here and then down here? It's like, because when I pulse up here, I'm at the E0 or I'm past the E0. And so, yes, I'm waiting for it to decay, but where it lands is the sum of background non-Faradaic and Faradaic processes. But at the bottom of the pulse is before the E0. So where it dies down has no Faradaic current. It has only non-Faradaic current. So let me kind of explain. Alex does a great job with this.
I can show you the
stuff you do better. You did a great job in your webinar.
Yeah.
With showing I'm at this potential. If you have those slides, that would be really helpful.
Yeah. So this.
Yeah. This is a great question.
All right.
Because conceptualizing this is really important. So this isn't square wave, but anyway, take it away.
Yeah.
Alex.
Yeah. So this isn't square wave. It's differential pulse.
But it's the same thing.
It's basically the same thing. The only difference is that these pulse widths. I know it's like I'm kind of like if I zoom in a little bit to see it. It's like basically in square wave, this length and this length are equal to each other. And other than that, that's the only thing. Like this just pulses. This is just a small pulse and this is long. But the concept is the same. So if we have this reaction, A is an oxidation reaction. A is going to be plus an electron. The E naught is, say, 500 millivolts versus silver chloride. And we assume that we have very fast kinetics. So if I say that my potential is like 500 millivolts versus silver chloride is located here, in this area, as I pulse the potential, at this point I have no Faradaic reactions, double layers charged. I also still have no Faradaic reactions, double layers charged, and I'm taking the difference between these two currents at these times. We call it I of tau and I of tau prime. And so it's kind of like, all right, you're taking the difference between these. They're a little different in time for a differential pulse, but it could be similar for square wave. But you end up getting very little in the way of current. If you were to take current here, you'd be getting all this extra current from double layer charging, right? And so this is part of like in chronoamperometry. You need to understand, this is where the 5 RC kind of comes from, but we already talked about that. And so skip all that stuff. All right. So now as we move from this area, that represents here. But when I'm in this area, when I'm near the E naught, here, there's no Faradaic reactions, and the double layer is charged to this potential. When I pulse here, I'm at a new potential, which is actually closer to the E naught. It's close to the E naught. That means that according to the Nernst equation, I'm going to have a change in the ratio of A and B, right? Because this potential here represents a significant change in this concentration. So that's what the new E is. And so if I think about this, my concentration profile between my potential at E1 and my potential at E2 is now different. So now I have concentration. I now have current flowing in this region. So this is the oxidation of A to B at E2. It results in current flow. And as a result, we end up getting extra current at E2 versus E1. Right? So before the pulse, this was what our chronoamperogram looked like. This is like the one step that you're talking about. And after the post pulse is E2, and we actually have a higher current. And I think I had some, yeah. And again, we're taking these tau values here. And so when I do that, I now have a non-zero positive difference between this guy and this guy. Before I didn't have that because I wasn't close to the E naught. But now I am. And so that means I'm at this part of like, this is differential pulse, but this is like my difference current. I'm at this point in the waveform. And this applies the same to square wave. And if I keep doing this and I relax and I go up, I keep getting these new potential waveforms, or these new concentration versus distance waveforms. I know I'm going through this very quickly, but you can see that like, oh, I actually have a little bit of current here, but my E4 is now much higher in current because it's much closer to the E naught of my redox reaction. So at E4, I have way more current than at E3. If I do the same thing, and now I have this much higher, way more current than this one, and I'm subtracting this, we now have a larger difference, a larger delta I between these two. Between comparing E4 and E3, this guy, E4 and E3, versus E2 and E1. And because that current is larger, the differential current is higher here. And as you can imagine, it just keeps on going. So I don't want to take up too much time, but that, and let's see. So
yeah, he says, I understand you're trying to cancel the settled current to take care of the polarization of the charge transfer, basically, but it's not related to capacitive charging current. I guess that's probably correct. I think what he's saying is the capacitive current is being canceled with this subtraction, but the difference is probably more related to what you'd call the polarization or the charge transfer process, because that's the Faradaic, the difference in the Faradaic current, what you're showing.
Yeah. There is it's like, that's right. And I did mention this a little bit in my webinar, where it's like, we say that we use these pulse techniques like differential pulse and square wave to cancel the capacitive current. The capacitive current is only canceled in the sense that we wait long enough for it to dissipate, right? That's it. That's truly it, especially for square wave, because you're kind of waiting the same period of time in both square wave versus differential pulse. So that's right. The difference between those two shouldn't actually cancel any capacitive current. It only cancels the non-Faradaic background current. Like if you're accidentally oxidizing copper in the background and that's contributing, it's like, well, that's gone because it's the same current, it's being canceled. You're only looking at these differences. So I think he's got it.
Yeah, I think that sounds right.
I think you understand. And no, you don't have to take a lot of our time. That we do this because people have questions about pulse techniques.
And I think it's reasonable to think to yourself, based on our explanation, hey, I'm going up and down, and I'm saying it's the same because I waited. Why isn't it always zero? It's a good question. Pulse techniques are weird, and they're hard to conceptualize. So you don't have to anything to apologize for. I hope that you have a little more clarity on this.
Yeah.
and it takes time to kind of think it through.
And that PowerPoint that I showed you is part of a webinar series I have on voltammetry. So if you're a tier 2 member on YouTube, you can watch the complete voltammetry series, but that specific section occurs on part 4, where I talk about like it's the quote advanced voltammetry, some coupled chemical reactions, but I talk about differential pulse, and that line of thinking is the same that can help carry you forward with square wave voltammetry. Square wave still has a lot of weird math, and the diffusion profile is a little odd, or the diffusion layer profile can be a little odd, but yeah, no, that should be helpful though.
Yeah. So we got a question from LinkedIn a little bit ago. Thanks for your patience. And we were kind of working through this pulse explanation here. But Abdulia says, I have a question. In some article for the optimization of the mechanical stirring speed, the curve increases, but they don't select the last stirring speed. And I asked for some clarification. Seems like you meant, like, were they talking about a rotating disc electrode or like a stir bar? And he said stir bar. So, I guess I don't totally understand exactly from the wording of the question either. Saying that like the article is about optimizing the mechanical stirring speed, but it wasn't the last stirring speed. I guess you're saying, it sounds like what you're saying is that they found that the curve increase. I guess I don't even know what that means. Like they're saying maybe like the current increases as the stirring speed increases, but then they didn't select the highest one or something. I don't totally understand the context of this question. I probably would need to see what paper is being asked. All I can kind of say are just a couple of things, which are that stirring the solution creates convective mass transport, usually. It depends on the geometry of your system. So for instance, I asked about a rotating disc electrode mainly because I probably could pull up a webinar real quick. I'm going to pull up a slide that probably better illustrates than what I could just draw offhand, which is never good. Let's see. So that is the picture I want. Okay. So just as an example, pull this up here. I asked about a rotating disc electrode because, for example, when you have an electrode like this,
the question. There we go.
You see, for instance, the tip of this electrode is something like this, where you have a disc or a disc in a ring electrode, and it's like at the bottom and it faces down. So when you rotate this electrode like this, what you do is you force the solution, like these lines, towards the surface of the electrode. Okay, when you rotate it, and so in this case, with a rotating electrode system, as you spin the electrode, you will get more current. Again, you say curve. I kind of don't know exactly what the paper you're referring to they're looking at, but generally the performance in a lot of ways just improves as you spin faster. With a situation of a stir bar, very often, I mean, again, it depends on the setup. I'd have to know what their setup was. But if you have like a solution with, your electrodes in it or whatever, and you have your solution, and now you have a stir bar at the bottom that's spinning around, right? Well, if this right here is your working electrode, right here, right? I mean, and you're spinning at the bottom in your stir bar, well, the solution is going to be drawn down. It's being drawn this way. The solution just fundamentally kind of flows to the object that's rotating, that's spinning. And so now you might get like better current or better, I don't know, performance or whatever, but the solution is not being like forced towards the working electrode. It's being forced, like in some cases, away from it, right? And so in this case, you have this situation where it's not obvious, perhaps, what the performance should be. So when you said, again, I can only answer with sort of somewhat vague answers because I don't have the paper you're referring to. I don't exactly know what you mean per se, but like, why didn't they select a certain speed? It's like, well, maybe because it's not a perfect solution, which is that like I can just rotate faster and faster and everything gets better. Because while I'm adding convection, which in some cases can force solution, faster to my surface, can get me better performance, more current, more products formed, all of those things. In some cases, if the convection is like away from my electrode, then it won't be best to just stir infinitely fast. And so there might be some, that's why, hence the idea of optimization. Like maybe there's some critical rotation rate at which it's like you get the best possible performance, but then rotating faster doesn't help. And then the other reason why is that as you rotate really, really fast, in a lot of cases, you can get bubbles. Cavitation is the word that's used sometimes. But if you rotate really, really fast, this like you can whip up the solution, and then all kinds of craziness happens. So I'll quickly get away from that amazing drawing. But as you spin and rotate faster, especially with a stir bar, I mean, you can just observe this. Like you can get like almost like a tornado, like a vortex, like of solution. And then if that creates bubbles and turbulence or whatever in your solution, you can have some problems with the electrochemistry because it can break the electrolyte interface. The gas can get on the electrode, cause problems, things like that. So that could be another reason why, for instance, the optimization, so to speak, of a rotation or a stir bar rate would not necessarily lead you to get the fastest possible spinning. That might not be ideal. And that could be some of the reasons. So feel free to follow up if you want, if you can, if you're still here. If you want to provide the DOI of the paper, I could look into it maybe briefly or at another time. Of course, you can always submit on our website, as I said. I can look into this more, but I would have to have a little more information.
Yeah. All right. Next question. Jenny Mentor 191. How temperature sensitive is the SEI, and can it have an effect on the voltage? Trying to understand the difference as well between charge transfer resistance and interfacial resistance. I'm assuming temperature does play a role.
It can.
SEI.
Yeah. I think it. I think it can affect the thickness, but I don't know exactly to what extent or like how badly that can be the case. So for instance, if your temperature is, I don't want to say it backward. I don't know, is it, my inclination is to say that if the temperature is higher, one of the things, for instance, that can happen is that the SEI can collapse. That's one of the things that can lead to thermal runaway, because the SEI is a naturally protective layer on the electrode in a battery. If it collapses, then the electrode is in direct contact with the electrolyte, and you can get a lot of decomposition and things like that to happen. So as the temperature rises, if it causes decomposition, or I don't know if decomposition is the right word exactly, or it can cause the SEI to collapse or whatever. Whether that's because it's too thick or too thin, I don't totally know, but it can impact things. As far as other, differences in terms of at different temperatures, how well a battery performs, I don't know how attributable those are to the SEI by temperature. So if the battery performs, let's just say better at 40 C than it does at 25 C, I don't know to what extent you would attribute that to the SEI being thinner, thicker, better, worse at 40 compared to 25 C, or it's the kinetics are faster because the temperature's higher, or something like that, like the electrolyte viscosity is lower, so it like diffusion is faster. Like I don't just like I don't know which of these things contributes most to the better performance or worse performance, and whether you would say it's the SEI or not. All I can really say again is that at really high temperatures, one of the things that can lead to pretty catastrophic failure of a battery is the SEI can collapse, and that does tend to happen at higher temperatures. As far as the voltage is concerned, this is one of these open questions. It's like Alex has talked about this, where it's like the potential at the double layer or whatever would be the same as the potential of the electrode surface. Mm-hmm. I don't know if that's exactly the same as like because the SEI is a little thicker. Like I think it's thicker generally speaking than like the electrical double layer. Like the electrical double layer is really pretty thin. It's what's nanometers, right?
Yeah.
So the SEI is certainly thicker than that. I think it's probably at least hundreds of nanometers to microns. Mm-hmm. I have to look it up again. I mean, I probably have some references of it, but it's thicker, pretty sure. So I don't know if that means there's a voltage distribution or like a voltage drop within the SEI. There probably is. Mm-hmm. You could probably calculate that actually, frankly, because you talked about the difference between the charge transfer and interfacial resistance. Like if the SEI has a appreciable resistance, you could think about an IR drop. I mean, you could literally calculate it. If it has a resistance of 100 milliohms, and you're putting 1 amp, that's 100 millivolts. That's extreme examples. I don't know if that's those numbers just made up, but just to think about the math, then you could think that there's actually 100 millivolt drop through the SEI, for instance, in that example, and then you would say, well, yeah, there is a voltage across the SEI that spans about 100 millivolts worth. Like something like that is a sort of rudimentary kind of calculation you could make as an example. But there's probably also studies where people have done like tried to do in situ studies of the SEI. It can be tricky because the SEI kind of exists like while you're running the battery, and it doesn't. Sometimes I think people have like taken the battery after it's tested, like take it apart, put it under a microscope, and hopefully the SEI is like still there, but maybe it's collapsed. So it's like the SEI is a hard thing to like get a lot of these like studies on, I think, because it's kind of a phenomenon that exists like under operation. So sometimes I guess I'd say a lot of the measurements with it or I don't know what you call it, like descriptions of it are sometimes more theoretical, if you will, like exactly what it consists of and those kinds of things. A lot of these papers that show what it consists of are, in my opinion, appear to be largely theoretical. Like, well, there's these oxides and these carbonate species and these and that, but it's like, I'm not sure we exactly know. Some people have tried imaging it. Some people have tried doing, microscopy and analysis, but it's like, it's not as easy to do that as a general course of research. So some of the answer to your question is difficult to know because the SEI is a little bit difficult to know with like perfect knowledge, I guess. What its voltage characteristics are, exactly what its its properties are. But hopefully that talks through some of it for you.
Yeah. All right. I think going to the next question, just asks how to cover bioelectrochemistry. Well, if we were to cover that topic, I mean, that's like many PhDs worth of knowledge there. Shelley Mintier would probably be the best person to talk about bioelectrochemistry.
Yes.
I don't know if there's actually a book on bioelectrochemistry. I think it's.
I feel like there must be, right? I mean,
I feel like it's. Let's see. Yeah, there is a bioelectrochemistry book.
look at that.
Bioelectrochemistry: Fundamentals, Experimental Techniques, and Applications. So I'm gonna put that in the chat in case people want the book on that. I don't know enough about bioelectrochemistry. I just know it's I want to say it's still a relatively new field. It's a very small aspect of electrochemistry. It is growing. There are some research groups doing stuff on that, but yeah, that's all I'm going to say about bioelectrochemistry. Unless Neil, you have anything you want to?
I know almost nothing about bioelectrochemistry, so I
Yeah.
have nothing to offer.
Yeah, we're sorry.
Yeah, I don't have a lot of good knowledge of that. All I know, bioelectric, like I guess, what's it? Microbial fuel cells is probably you would classify as bioelectrochemistry. I'm guessing, microbes and and fuel cells is electrochemistry. And all I really know about microbial fuel cells is that my advisor hated them. So we did some like proton and alkaline uh, acid and acidic. Geez, words are hard. Like alkaline and acidic fuel cell type research when I was in graduate school, and microbial fuel cells were not part of our portfolios or whatever. So they were not well regarded in our group, I guess.
Yeah.
Which that has nothing. That doesn't invalidate anybody else's research. It's not something that I got into. The only thing I can say about bioelectrochemistry is that another reason why it's really difficult is that working with biological material is just really hard. Like you deal with inconsistencies, biological samples, in general can be difficult to obtain. Is it human samples, animal samples? It's biological material. It's like, right. So it's not always convenient or reproducible as easily. So there's some challenges with it to be fair. It can make it really difficult.
Yeah. Okay, moving on. Last kind of 15 minutes ish of time. I have another question related to open circuit potential. I know that it can help in getting to know the concentration, but how is it really different or better with respect to amperometry? Does it increase cell life? So the open circuit potential, it can only really be used to determine concentration if you know what if you know the E naught of your system and then its open circuit potential, and then figure out what the concentration ratio is through the Nernst equation. But the open circuit, like when you use a technique like chronoamperometry and you're relating the current to like the concentration as a function of time, then that's generally what people use when it comes to figuring out how much current they have in a particular system for chronoamp. Open circuit potential is not really used that much to determine the concentration of a species in solution. Open circuit potential is nice because it's kind of a non-destructive technique. Not that electrochemistry is inherently destructive, but like you're not applying huge currents, you're not applying huge voltages. You're just kind of passively measuring what the voltage is of your system and then inferring information from it. So when it comes to things like increasing the cell life, I don't think it plays too much of a role. I mean, the open circuit potential is just the quote potential open circuit. When there's no current passing through your cell, what's the potential? That's all it really is. But amperometry, you're usually applying a potential and measuring a current response as a function of time. So you are perturbing the system in some kind of way. So those are the few things I would mention with regard to the open circuit potential and concentration and amperometry. Hopefully that's kind of helpful. Next question. When measuring proton conductivity, PEIS, of a polymer film, why is grounding the system not necessary? When would grounding be necessary in EIS?
Grounding is really something that's a trial and error kind of procedure, I guess. It's not always obvious why. Sometimes the answer has to do with if you have really low currents. In general, with very low currents, they can be systems can be highly susceptible to noise, and having proper grounding can eliminate that noise. This can be things like adding a Faraday cage around your system, which is basically just putting your whole working counter reference electrode, everything inside of a big metal box. And then often the grounding configuration consists of connecting the chassis or the box, the metal box of your potentiostat itself to that Faraday cage. You connect those chassis together. So it creates one kind of big shield around the electronics of your potentiostat and the electrochemical system in the cell, which would be your polymer film, I guess. Other times it's requiring a floating situation, which is where you make sure that there's no earth ground connection. So like the third in the US, it's like, or a lot of countries that have similar plugs. There's the 3 plugs, right? So my thumb here would be like the ground, the thick, third prong or whatever on the power. By default, most of the time, that plug does not make connection with your potentiostat in any way. It's isolated. But you just want to be sure you don't sort of by default, if whatever potentiostat you're using, if it has a grounding wire, you need to know there's 3 kinds of ground. You need to know what the ground like connection, like sometimes cell cable potentiostat cell cables, have a ground line right on it. Sometimes it's usually a black or a gray line. I guess it depends on the potentiostat company, but there's often a grounding line. Well, there's 3 types of ground, broadly speaking. And so it would be important for you to know, if you're thinking about grounding strategies, which type of ground is that? There's earth ground, which is literally the planet. It's that the third plug goes to usually in a building. It's like it's connected electrically to like a pole that's jammed into the earth, or that goes directly to the earth. That's earth ground. There's chassis ground, which is, as I said, it's the metal box surround of the potentiostat itself, which is around all of the electronics. That's called chassis, CHASSIS. You give it like the chassis is the word used for like a car. The body, the metal body of a car is called the chassis. The third type of ground is called DC common. This is a 0-volt reference point on the circuit board of the potentiostat. Now, very often, the ground cable of your potentiostat cell cable is DC common. It can or cannot be helpful to connect that to earth ground or to chassis ground, but it just depends. It's not a guarantee that matters. Some potentiostats by default have the chassis and the DC common shorted together. Sometimes that helps, again, in some situations. In some situations, having everything floating, which is to say nothing is connected to anything. Chassis is totally isolated. DC common is totally isolated, and there's no connection to earth ground. That's fully floating. In some cases, that can be better for very low currents. So, for instance, if you have your impedance measurement is of your system with a very high impedance. High impedance means it will have low current, and low current means it can be susceptible to this kind of noise. So if that's your case, grounding might be important. But if you have, let's just say what I would call normal kinds of current measurements, microamps or milliamps or higher, very likely the grounding situation won't make any difference at all. So as a general rule of thumb, think about if your current is very low, grounding might make a difference. If you're experiencing noise that can come from anything from physical vibrations to other equipment nearby, to electrical equipment, to the lights in the room, things like that can be, you can mitigate a lot of that by using a Faraday cage. That can help reduce some of that external noise. There's other things you can do, like twisting of cell cables depending on the frequency range you're doing. But ultimately, most of this kind of stuff is trial and error. And if you're suspecting that noise is a problem and you tinker with a lot of grounding stuff and it doesn't seem to change your results a lot, most likely you're not in a region, level of current, if you will, where the grounding really matters. So trial and error is always going to be mostly your best friend, but you almost can't go wrong putting a Faraday cage as long as everything fits, like, get a big enough box and whatever. But a Faraday cage is almost always going to help in a lot of situations, just because it'll help filter out any just electrical noise. And most laboratories have a lot of equipment, and there's electromagnetic signals, and there's even the fluorescent lights can sometimes cause some issues. So having a Faraday cage as a general rule can be a good idea. So that's talking. And the last thing I'll say is that on our, for example, my company's website, I'll just note one quick thing. You don't have to necessarily have our potentiostats, although I do recommend it because, well, I work for this company. But the user guide for our potentiostats documents. So here, for example, if you look at our workstations, so if you come to our website, pineresearch.com, and you just go to our workstations, you can pick sort of any of them. But basically, on the documents, we have user guides, obviously, for our potentiostats. You can download the user guide. These user guides have a section in them that talks about grounding specifically. So I just wanted to mention that you can download those. You don't need to buy a potentiostat to download the user guide if you want. There's talks through all of these kinds of things that I just mentioned. So strategies of grounding, you might find that useful.
All right. And one more question, which is, does SEI formation consume any charge, Coulombs? I'm trying to apply Faraday's law to a symmetric lithium cell while applying a known current, but I'm wondering if the total charge is more than I times T, or I times time.
So yeah, it does consume Coulombs, but it's not going to be like imaginary mystical Coulombs you can't account for. Like,
yeah,
it sounds
part
like
of the I times T.
Yeah, it's going to be part of that. It sounds like you're thinking perhaps there's like an unaccounted for amount of Coulombs that are taking part in the SEI formation. It's like, no. The SEI will be formed electrochemically during the, I assume, galvanostatic step that you're doing. But either way, whatever you're doing to your cell, by passing current into it over some amount of time, some of that current or charge will go to the SEI formation for sure. It won't be likely every time, which is why you're working with a lithium cell, symmetric cell, so there might be some differences in how it functions or whatnot. But basically, the first one or two maybe cycles, usually with a battery, is where the SEI forms. And after that, it's in place, so to speak, and so you shouldn't get a lot of charging. You shouldn't get a lot of charge associated with SEI formation in subsequent experiments. But at the very beginning, there will be some. There should be some. It says I assemble the cell before applying the current. Okay, so I'm wondering if there was a charge that got consumed that I didn't quantify. The SEI is not likely to set up on its own.
Yeah.
So it's gonna like it's a redox process. Usually, I think a reduction process most of the time. So, before cycling, I don't believe that can really happen. You'll get like any electrode in like in an electrolyte electrochemistry system. There's some surface state, there'll be some surface condition that will exist, so to speak. There'll be some potential associated with the surface or whatever. Like those things will happen. but the SEI specifically, the solid electrolyte interface, whatever you want to call it,
It
that
doesn't spontaneously form.
yeah, that's not going to spontaneously form. That is an electrochemical process by which the electrolyte partially decomposes and forms a film interface layer right on the typically the anode in a battery that further facilitates transport of lithium ions, in this case of lithium, and prevents subsequent decomposition of electrolyte and keeps the battery stable. And that requires an electrochemical process to form. So certainly it looks like you're on the right track. You're thinking things through properly. You're like looking at the charge. You're trying to figure out, you might have there might be some errors. There might be some, just it's batteries. Like it's going to take trial and error. It's going to take time to figure things out. But I would not think that one of the mistakes or one of the differences in your calculations is because the SEI is spontaneously forming. I don't believe that can be the case.
Mm-hmm. All right. There is it's kind of a one last little interesting question, which is a book to understand battery and know everything.
Know
from
everything.
The basics. And I don't know if there's any books that can know everything.
Sounds like a really deep question. How do I know?
Yeah, it sounds like
basics?
And encyclopedias. I mean, they're like.
If only someone would like finish putting together the battery webinar that they've been trying to finish for like 3 years. Someday
everything about.
Yeah.
It'll be everything about batteries.
It's not going to be a book, but it will be a webinar. So Ron Chatterjee, I've been in the process of putting together a battery webinar, and a variety of things have kept me from putting a lot of effort into it in the last several months. But I still have plans of finishing it.
Yeah.
And it's already May, and I don't know where the time goes, but things happen, and at a company, your priorities and your development, get diverted and changed for long periods of time, and then all of a sudden you look up and it's like crazy. The webinar that I'm putting together is going to cover a lot of the basics. I guess I'm planning on it. I'm trying to do it from that perspective. Again, not a book, but it'll be a webinar, and I don't know, maybe that works for you for what you would want to watch or consume. The webinar will be free. It will eventually be. Please do it fast. Yeah, I know. Look.
Yeah,
I can't explain it to you on the live stream. Alex knows what I'm talking about, but I had plans of working on it all this year, and that has basically not happened for a lot of different reasons. Yeah. But I do have a lot of materials for it, and I will do my best to get it out at least by the end of this calendar year, because I still want to. I'm still planning to do it. So stay tuned. Check our website. Our website. We have a webinars.
Well, he'll be waiting.
He's going to be waiting for at least a little while longer. I apologize.
Ominously.
Yes, we have the webinars tab on our website. That's where it'll be for registration. Once I have it ready, I'll try to send emails and stuff like I usually do to announce it. We'll announce it here on this live stream. You won't miss it, I promise. If you're paying attention to us in our company and stuff like that, we will be very open about it. It's just, again, it's not worth getting into on a live stream, but there's been a lot of different things and other tasks that have taken me in my need away, and I haven't been able to develop. I was working on it a lot leading into the early parts of this year, and I had to move away and do other things. So anyway, that's it.
Yeah.
But
it's all good.
I promise I will have some battery basics webinar content for you relatively soon.
Yeah. Okay. All right. Well, very good. We are at time, basically. Yes. And for that, we'll see you all next week. And come next week with your questions. Most importantly, use the website. Go to pineresearch.com, use the message system, and then say you have a live stream question. We prioritize those questions above all the other ones. So if you send us a thing on the live stream chat, or if you send us a LinkedIn message, or if you send us an email, We'll get to those, but the ones that we get to first show up as a message in using the online web portal.
Yes.
All right.
And you can put the DOI of your paper. You can put a plot if you want us to comment on a graph that you can show rather than just explain. Give us some context. We can hopefully do a better job in some of those cases, understanding what you're asking. So
yeah, absolutely.
All right. So until then, I guess I hope everybody has a great week. We will see everybody next week, and we look forward to your questions, I guess, right?
Yep.
Cool. All right. Well, take it easy, everybody. Thank you.
Bye.